webinar sponsored by PCTEL. My name's David Newman. I'm the GM for RF Solutions Group at PCTEL. As many of you may know, PCTEL has been developing LTE scanning receivers for some time. We delivered our first LTE scanning receiver more than 5 years ago. The units are used globally for both FD and TD networks. Joining me today is Jim Zick. Jim is our Senior Product Marketing Manager responsible for PCTEL's scanning receiver product line. Jim has more than 20 years experience in test and measurement. And for those of you that like the LTE posters or have ordered the LTE posters, those were Jim's creation. Before I turn this over to Jim, we have a few housekeeping items. We welcome questions throughout the presentation, but please post your question in the question box on the right-hand side. We'll collate the questions and then we'll go through them at the end of the presentation. So again, I'd like to thank you for joining, and I'll turn the presentation over to Jim.
Thank you, David, and good morning, good afternoon, or good evening, wherever you may be in the world. My name is Jim Zick, and what we're going to cover today are first the LTE physical layer measurements that are important for measuring what's important in your network. That'll be followed by an LTE drive test case study. Then after that, we'll cover an LTE MIMO analysis case study, and then provide a summary of what we talked about today. So first, let's move on to what an LTE frame and what an LTE channel bandwidth is all about. And really, what's important here are the reference signals. What I'm showing you here on the left-hand side of the chart is a 20 megahertz channel bandwidth. And essentially what it's supposed to represent is an LTE frame. And if you look at what the reference signals are, they're actually, every one of those little black squares in there is a resource element, and the reference signals are scattered throughout the whole channel bandwidth. So what's really important here is that the reference signal, which is used for self-search and channel estimation and neighbor cell monitoring, that you actually measure each one of those reference signals as opposed to just measuring maybe, like some scanners do, the center of 1.08 megahertz. It's really important to measure that full channel bandwidth and looking at all those reference signals, because a lot of things can happen at the edges of that. You can have interference. You might not have flatness in your power amplifier. So consequently, the ability to look at the full channel bandwidth is something that's very important when you're measuring the reference signal in an LTE network. So moving on to the next slide, what I want to talk about here is the critical measurements for an LTE network. And these apply both to TD as well as FD LTE networks. So the first one I want to talk about is the RSRQ, and this is measured in dBms. As you can see in the little diagram on the upper right, you can see where these reference signals are kind of scattered throughout the resource block. What I have pictured here is actually two resource blocks. In a 20 megahertz channel bandwidth, you'd actually have 100 of these. So essentially what RSRQ, which is one of the most critical measurements, is a linear average of the power of the resource elements that carry the cell-specific reference signals. And as I mentioned before, it's measured across the entire LTE channel bandwidth. And if you're familiar with WCDMA or UMTS or CDMA and EVDO, it's the equivalent of what they call EEC in these other technologies. And the applications for this is really to measure what your power is for these reference signals. So what you're looking at is the if there's any path loss in your downlink, you have the ability to look at sub-band level path loss, identify, what your sector service area is by looking at this RSRQ. As you get out of the sector, that RSRQ should drop drastically. And be able to determine the signal strength as used by the network for handovers. So this is one of the critical measurements for an LTE network, whether it's TD or FDD or FDD LTE. Moving on to the next slide, what I want to talk about here is the RSRQ measurement. Just like RSRP, this is a 3GPP standard, and it tells you exactly how to take this measurement and what that definition of that measurement is. And this is a relative measurement, so it's measured in decibels. And what the definition of this measurement is it's the number of resource blocks multiplied by the reference signal resource power. Those are the, again, the measurements that we have taken in the last slide, or we described in the last slide. And this is divided by the EU Tricarrier RSSI. So this is an important measurement because this is really used for handover operations. And like RSRP, it's measured across the full LTE channel bandwidth as well as the selected subbands. Some of the indications, or I should say the applications for this, is that it really determines the coverage with respect to loading, because RSRQ is actually dependent on the amount of traffic that is on the network. So when you have a lot of traffic on the network, and we'll talk about this a little bit later, the RSRQ actually drops, which is used by the network to indicate that you might have a handoff condition, and you can perform a handoff based on this. So this is measured both in scanners as well as in UEs or data cards, and the two measurements are essentially equivalent. This is the 3GPP standard. It's not necessarily a good indicator of signal quality, though, and we'll talk about that on the next slide. Because on the next slide, what we're moving on to here is the CINR or SINR measurement. And what this stands for is the signal to interference to noise ratio. In our case, we actually call it the carrier signal to interference to noise ratio, which hence it's called CINR. Again, it's a relative measurement, and it's measured in decibels. This is not a 3GPP standard, however, so if you have different types of scanners or UEs, they may calculate this measurement slightly differently. So the definition of this is it's really the ratio of the RSRP, which we already talked about, and the interference and noise that are coming from that same reference signal set. And again, this is measured across the full channel bandwidth, whether you're at 1.4, 3, 5, 10, 15, and 20 megahertz. Now, the reason why this is a very important measurement and why customers really rely on this measurement is that it's a really good indicator and a much more stable indicator of signal quality than RSRQ. It's much more sensitive than RSRQ to variations in the level of interference and noise. So if you look at the formula here that's shown, you have RSRP divided by interference and noise. As soon as my interference or noise rises, my CINR goes down. It's the equivalent of what you would see in WCDMA for a SNR measurement. The reason why this is really important is because you can benchmark signal quality with this. You can actually use it as an estimate for some of the physical layer throughput rates for single antenna systems by doing a simple translation. And you can identify signals that are poor quality, and in combination with RSRP, you can determine and identify whether the signal quality problems are caused by interference and noise or not, and allows you to identify intercellular interference problems. So this is a very, very important measurement. It's also a very difficult measurement to do accurately, which is hence why scanners are used to do that. Because what we've actually seen in some cases, the difference between a UE and a scanner can be much as 7-8 dB on a CINR measurement, with the UE not being very accurate when it comes to this measurement. And what I want to talk about on the next slide is the difference between RSRQ and CINR. As I mentioned before, that RSRQ it changes with traffic loading. And if you look at a blow-up of that resource block, it's actually two resource blocks there, and you look at how that formula is calculated, you see that you have, for RSRQ, it's the reference signal, which in this case I used R0 for simplicity. I'm only using one resource element. And it's divided by the EU-TRA carrier RSSI, which is everything in that red rectangle. And those gray boxes in that red rectangle is actually traffic. So as my traffic increases, my denominator gets higher, my RSRQ goes down. So it's not really a good indication of what the signal quality is for your propagation models. However, it's very useful to determine how the network is reacting when it comes to traffic handovers. But this is why CINR or SINR is really used as a measure of signal quality, because the way this calculation works is I'm actually taking that resource element, R0, and I'm actually dividing it by the noise and interference in that same R0 location. So this is a great indicator of what my actual signal quality is in the network. And hence, this is why CINR is used by a lot of RF engineers for measuring the quality of a LTE network. And if you're familiar with WCDMA or UMTS, a lot of people didn't use SNR. What they really used was the actual power, like EEC, or in some cases DC over I0. But SNR wasn't very popular, unlike with LTE. Pretty much most RF engineers combine RSRP with CINR as major measurements for determining the quality of that network, as well as for engineering that network. On the next slide, I'm going to talk about path measurements. So in a typical LTE system, you usually have multiple antennas transmitting. In most cases, it's two for now. And what I'm showing you here in the diagram is what they call 2x1 transmit diversity. And in this case, what you have is two transmit antennas on your E node B or on your tower. And they're actually putting out separate signals into a single receiver on your UE. And again, this is called transmit diversity. It's one of the transmission modes. In the case of MIMO, you might have what's deployed today typically is 2x2 MIMO. So you have two receivers or two antennas on your UE, just as you would on a scanner if you're doing MIMO measurements, to be able to collect those measurements in each separate path. What you really want to do is to be able to determine the power, the RSRP, the RSRQ, and the CINR, the same measurements we had talked about before, on each one of these paths. And that's very, very important because it helps you identify whether you have cross-connected or disconnected antennas. And it also, when you combine them with MIMO parameters, it can help you diagnose MIMO performance issues and throughput issues by looking at each one of these paths that go from your transmitter to your receiver on your LTE network. Another important measurements are the ability to do LTE Sub-band measurements. So if you look at what I'm showing you here, I stacked up a series of 4 resource blocks. There's actually 2 resource blocks shown in each one of those little boxes. So this is a total of 8 resource blocks. But essentially what you're doing with sub-band measurements is if you have a 20 megahertz channel bandwidth, you will have up to 100 resource blocks stacked up on top of each other for all these subcarriers that are within the LTE frame. And by having the ability to actually go down to the sub-band level and looking at 4 of these different resource blocks, a group of 4 at once, you can analyze whether you have any frequency selective fading that might occur at the edges of your channel bandwidth. Or, for example, if your power amplifier is not flat, you'd be able to see whether or not you have an issue with that. And it would help you be able to debug problems that you might have with your LTE network if you have customers reporting an issue. So this can be a very important feature when you are looking at an LTE network to be able to debug issues that are hard to find. On the next slide, I want to talk about TD-LTE a little bit, and I know for the most part what's deployed today is FD-LTE, but TD-LTE is coming on strong, particularly in some of the Asian countries and even Latin American countries. And essentially what the difference between FD-LTE and TD-LTE is that FD-LTE has what we call paired spectrum. So you have a certain amount of spectrum for the uplink and a certain amount of dedicated spectrum for the downlink. With TD-LTE, you have unpaired spectrum, so you're using the same spectrum for both the uplink and the downlink. And the way you separate the uplink and downlink is based on time slots. So what we're showing you here in this diagram are the uplink and downlink configurations that are defined by 3GPP. And what they define is from 0 to 6. And you have what the you call the subframe number that goes from 0 to 9. So what you can do is you can control the amount of uplink and downlink you have. And if you look at that diagram, for example, with configuration 0, I can have 3 subframes, or I should say 6 subframes of uplink and 2 subframes of downlink with a couple of special subframes for the guard band. But as in most networks, you probably have more downlink than you have uplink. So you might want to set your uplink downlink configuration to maybe a 4 or a 5, where I have a lot more downlinks than I do for uplinks. And what you want to be able to do is that whole network in the region has to have that same uplink downlink configuration number, because if I don't, wherever there is a edge between where the uplink and downlink configuration changes, I can have interference where the downlink and uplink are interfering with each other. So being able to measure that uplink downlink configuration can be very important to verify that the eNode Bs are using the correct and the expected uplink and downlink configuration. And if you use it in combination with some detailed features we have like on scanners, like an LTE power analysis, you can help determine what the best uplink and downlink configuration is for the type of traffic that you have in that network. So TD-LTE is coming on strong, and uplink downlink is a very important measurement to be able to understand how that network is working. So there are also other measurements I'm not going to talk about because I just want to cover the important measurements, but there are other measurements such as time offset and delay spread and layer 3 measurements. But what I really want to do now is to move on to some of the case studies that we've actually done for LTE, starting with the LTE drive test case study, followed by MIMO analysis and a summary. So let's begin with a drive test that we did back in April of this year. The area that we drove was downtown Philadelphia. And the equipment we used was a PCTEL MX scanner with all the measurements, including layer 3, MIMO, CDMA EVDO. We also, we're only going to show you the LTE measurements that we take. We're not going to concentrate on the other technologies. We also had our Seahawk drive test software to run the scanner. We had a competitive scanner that measured LTE, as well as a LTE data card, also known as a UE. So the measurement factors that really differentiate the different scanners as well as the UE. Number one is speed. Speed is very important because you want to be able to look at fading issues. If you don't have enough data to look at fading issues, you're not necessarily going to know what's going on with your network. You need very high dynamic range to provide analysis of interference from other sectors and what other servers are entering into the sector. We want to have good detection accuracy, be able to minimize false detections. We've seen some scanners with false detections of 10–20% when it gets down to very low CINR values or SINR values. And then have a lot of supported measurements. In addition to the ones I talked about, things like time offset, delay spread, MIMO parameters, layer 3 messages, to be able to really look at that network and analyze it for any issues that might creep up to be able to optimize that network. So first, on measurement speed, what we're comparing here is the difference between a PCTEL MX scanner and a data card, a UE. And the total number of data points we took was over 400,000 with the scanner. And with the UE, we collected about 50,000. So there's about an 8x difference, an 8 times difference. We got 8 times more data with the scanner than we did with the UE. And the average measurements per second, we got about 18 or 19 with the scanner, and 2 measurements with the UE. So the scan speed, this translates into about 54 milliseconds per measurement, and with the UE, it's about 1 measurement every half a second. So essentially, what we're able to do with the scanner is be able to collect 9 times as much data compared to what a UE does, as well as offer much higher detection accuracy. And at the same time, we're also collecting data on other technologies also, other than just LTE, and still getting this high data density. So on this chart, chart 16, what we're showing you here is the difference in the number of cell ID detections compared between the scanner and UE. And it's quite dramatic, actually. If you're looking at what's in green is what the scanner is able to detect as far as how many cell ID detections we had. And if you look at the red is essentially what the UE did. So essentially we had about 8 times more detections with the MX scanner. Overall average was actually about 10x. So this can be very important, like I mentioned before, when it comes to looking for fading issues and this type of thing, in order to be able to get as much data as possible of what your RF environment looks like. The next item is dynamic range, and this is really the ability of the scanner to decode low-power signals in the presence of high-powered ones. It helps in determining the complete propagation profile of every sector in your network. Very, very important for interference identification. And it also provides accurate detection of PCIs if you have very low CINR or SINR values, which is a key indication of dynamic range. So to move to the next slide, you can see, you can really look at the difference between the dynamic range between what a UE does and what a scanner does. And this is very dramatic on the low end, because this is really important in identifying what types of signals are entering your sector. And having the ability to reach deep down into that dynamic range and find out what number of detections you're having down at the low CINR values is very important in being able to optimize that network. So what we're showing here is a very good dynamic range on the MX scanner on the low end, and on the UEs in blue, you can essentially see again a very dramatic difference between what the values of a UE are versus what the dynamic range is for an MX scanner. And this is essentially one of the major reasons scanners are used, not only speed, but also this deep dynamic range to be able to identify which issues you have with your network and be able to correct those problems by finding out exactly what your environment looks like with the scanner. So now I'm going to show you a few of the maps that we did going on in this particular case study. So in this particular case, if you look at the upper left-hand side, we're looking at the complete propagation profile of the drive test that we did. And as you can see with the MX scanner, all the circles that are in red, you can see where the scanner actually picked up a lot of the details of what's going on in the network versus what in this case, it was a low-grade scanner was able to pick up. And it's quite dramatic. You can see again, we're getting a lot more detections with high dynamic range to find out what's actually propagating into these sectors versus what a low-end scanner is able to provide. And we can even see the backload propagation coming off the antenna with a high dynamic range scanner to find out what's really happening in that RF environment. So moving on to the next slide, what you see here are all the pins. What they represent is where the UE, the data card, actually dropped the session. And obviously when you drop a session, you're not collecting any data with the UE. So what we experienced was multiple failures during the entire drive. Every time you see one of these pins was a failure where the data card dropped. And when you're running data, which LTE is right now, you may not notice it as much. But once you start running voice over LTE or high definition voice, you're actually going to see dropped calls potentially at these locations. So what we did is we used a scanner actually to determine what the cause was of these data card drops. And that's what we're going to go through with on the next few slides to be able to understand what's going on, because you really can't do this analysis with the UE since you're not collecting any data anymore because you dropped the session. So the first thing we looked at on this slide was the number of services. So when you look at the previous slide, I had a little circle of what we wanted to analyze. So what we're analyzing here is like a 4x4 block area where we had 4 locations exactly where the data card drop service. And what we're finding out first is there's a very high number of PCIs detected in this problem area. And what this demonstrates is a lack of dominant carriers and presence of these carriers, which can cause a lot of interference. And if you look at what's circled on here in red, what we're seeing is anywhere from 10 to 30 PCIs. So we're seeing a lot of PCIs in this very small area, which is indicating that maybe this is a problem because we had some dropped sessions in this area. And our first indication is it's probably caused because we don't have a dominant carrier in this location. So then on the next slide, what we did is we looked at the best server cell ID. So what we're doing here, again, is the same 4x4 city block area. We're finding out in this very small area, which is about 0.3 of a mile. It's about 4x4 city blocks. We're finding 15 different best servers in a very, very small area. And this is indicated on this chart by the number of different colors you see. As you can see, there are a lot of different colors here. It indicates a different best server in a very, very small area. So again, what we're seeing is a lot of handoffs that are occurring in here, and hence probably some bad handoffs, which is why you're seeing some dropped sessions in this area. So what we look at now on the next slide is we wanted to dig a little deeper into this area and actually look at what the CINR or SINR is in this area. And we suspect because you have a lot of best servers and a lot of servers and a lot of PCIs getting in this area, you probably have too many high-powered servers, which is causing low CINR, resulting in failures. And indeed, we do see that in this case. So what we're actually seeing, if you look at what's circled in red, are a lot of very low values for CINR, anywhere from -10 up to about 0 to about 5 dB. So when you have a scanner with a very high dynamic range like the MX, it helps you understand the effect of too many servers and a lack of dominant servers, and its effect on CINR and the overall throughput. So this low CINR can also affect when you start to have voice going over LTE, which is something that will be coming up here in the next couple of years. So what we're really trying to show here is that a scanner like an MX can be very, very helpful to analyze real LTE network issues. So on the next slide, we want to show something else that looked very interesting also. Is we looked at where actually the best servers were coming from. And for a large portion of where this 4x4 block area is, we found that the dominant server, one of the major dominant servers, was actually a sector that was over a mile away and actually pointing in the opposite direction. So what's happening here is you're getting some reflection that's coming off of this, this antenna back into that area, and it's becoming a best server for that area, which is probably an unwanted best server for that area. So nearby sites are probably not dominant enough to be able to overcome the power of this, this one sector that's actually getting into this area. So in this area, what you have is actually characterized by very, very high buildings and multipath scenarios. So it's probably going to be a difficult area to be able to design optimally. But the fact that you have something that's getting in there that's over a mile away is something that really needs to be looked at to be able to optimize this particular area of the network. So with that, now that we looked at the LTE measurements, what I want to move now on to is the LTE MIMO analysis case study for that same area. And what we want to analyze here is to be able to look at the throughput in an LTE MIMO case study based on the same area of what we looked at before. So first, what I want to talk about are some of the MIMO parameters that are important for an LTE network, because it's really important to understand the MIMO transmission characteristics of the physical layer in the RAN as reported by a scanner. So we already talked about path measurements, and these are measurements, like I mentioned before, between each transmit and receive path. There's also what's called estimated channel quality indicator, CQI. This is defined by 3GPP. But what this is, it's a consistent indicator of the theoretical transmission physical layer efficiency. And then we have estimated throughput. And throughput, you provide an estimate for each of the various MIMO transmission modes, and this is based on the estimated CQI. So based on the CQI number that you are able to measure, you now look at the, you can calculate the throughput estimates based on what that CQI value is. And another important MIMO measurement is the channel condition number, also called the CN number. And the CN is a measure of the independence or the correlation of the channel paths. So like I mentioned before, we have like 2x2 MIMO that's deployed today in most, in a lot of LTE networks. And what you're trying to measure here is the correlation between those paths, between those paths that are originated on the two transmit antennas to your two receive antennas back at your UE or your scanner. What you really want is a very low correlation. This is measured in dB. You want it down around 0 dB. If you have it, you know, in the higher range, like 20 dB, that means you have high correlation, and you're not going to get a lot of MIMO gain as a result of that. So what we can do is we can use the throughput values and then go back and look at CINR and the condition number and find out what the reason for that throughput is based on those values. The other thing I want to mention is you have various transmission modes for MIMO. And I have 6 of them defined here. There's actually about 9 of them if you look at release 10. But the ones that are deployed today are the ones with the green arrows. You have transmission mode 1. It's not really MIMO. This is a single antenna, single receiver, also called SIZO. Then there's transmit diversity, which I showed before when we have the path measurements. In the example I showed before, you have 2 transmit antennas going into 1 receiver. You could also have it going into 2 receivers. But transmit diversity technically is not really MIMO because it's not doing spatial multiplexing. But then you have the other, what we call true MIMO transmission modes, transmission mode 3, 4, and 6, and these are various types of transmission modes used in MIMO that employ feedback mechanisms to be able to maximize the throughput. So what we're going to do is, what a scanner actually does is it will measure the estimated TQI on the physical layer only, as well as the throughput. So what we're looking at is only what's happening in the RAN, and this is very different from what's happening in the UE when it measures throughput, because in the UE you're doing it at the user layer, and it's going to be looking at the throughput not only from the RAN, but also through the backhaul and also through your server. So the causes of poor throughput won't necessarily be attributed to the RAN. They could be attributed to backhaul problems, or they could be attributed to a high server loading. But essentially what a UE does is it looks at the best transmission mode, and then it will actually convert over to the best transmission mode to maximize throughput. So this is the reason why in a scanner also we look at all these different transmission modes, because we can do the same thing, and we can look at what the best throughput is in any location based on what transmission mode is available. So let's look at the data card throughput that is on the next slide. And again, this is the same area in Philadelphia. And when we look at this, we see that the data card throughput it seems pretty low. It's around, it doesn't go above 5 megabits per second. And what we're finding out is that the network was actually capped at 5 megabits per second for the UE. So you're really not able to characterize what the actual throughput is of this whole region, because you know, it could have gone a lot higher if the network wasn't capped. So we also see some areas in the red circles where you have very low throughput. And these are areas where you're less than 1 megabit per second, as shown by the red circles. So on the next slide, what we're actually showing you here is the maximum estimated throughput of the RAN based on what the scanner reported, the MX scanner reported. And like I mentioned before, you're going to see a lot higher throughputs because, number one, this is a theoretical maximum throughput, and it's measured at the physical layer only, not the user layer that a UE does. And number two, it's not going to be capped, because what this does is it looks at what the RF environment is like, as well as what the MIMO parameters are like based on how the antenna and the CINR and how the antenna is set up. So consequently, we're going to report what the maximum estimated throughput is, what the environment is capable of putting out for throughput in an ideal situation. And the reason we do that also is because you want to be able to have consistent reporting from one day to the next, as opposed to something that, like a UE, that is actually dependent upon what the server is doing and what the backhaul and how it's loading. But if you look at the data here that we collected with the scanner, what you see is that the maximum throughput can get up to 60 or 80 megabits per second, indicated by the blue and greenish blue type colors. But we're also seeing some areas of low throughput in a lot of the same areas that you saw with the UE. If you remember on the previous slide, the UE reported under 1 megabit per second. So in some of the areas, the scanner, in fact, it's pretty much verifying those same areas where you have low throughput as the UE did. But in addition to what the UE can do, we can look at the whole network and find out exactly what that environment is capable of supporting. Now, on the next slide, what we want to do is look at what the effect of CINR is on estimated throughput. And MIMO is really dependent upon CINR. So if you have very low CINR, you're not going to get any MIMO gain. So what we did is we actually looked at all the data that we collected in this test, and we want to find out what the effect of CINR really is on MIMO. And indeed, you're seeing that your throughput is very low for low CINRs. But when you get about 20 dB of CINR or SINR, you start to max out what MIMO can do. So throughput is really saturated once you get above 20 decibels when it comes to the CINR. So essentially, what we're showing you here is that when you set up a MIMO network, what you really want to do is set a goal of trying to get a CINR of 20 dB or higher, because that will really maximize your throughput for a MIMO network, a MIMO LTE network. And CINR is what we would consider the most important parameter when it comes to improving throughput, even higher than condition number. So number one, you want to look at CINR, and then next, on the next slide, I'm going to show you what the effect of condition number is. So as I mentioned before, condition number, again, is the amount of correlation between the two signals coming from a MIMO system. And if you look at that same region again where we had low CINR values, and we had drop sessions with the UE, we found a high percentage of location points with a condition number of 15 or greater. Again, you'd like to be probably under 20 dB. And in the same area, the serving sectors where you have a high condition number, the CINR is also low, which overall affects the throughput adversely, causing failures. So what this tells us is that you really want to be able to go back in here and optimize this little portion of the network to be able to maximize your throughput, get your CINR values up, and hopefully reduce your condition number. So on the next slide, what we're looking at here is the effect of throughput as a function of CINR and condition number. So on the upper chart, as you remember, as I said before, when your CINR gets above 20 dB, you saturate your MIMO gain. So what we're showing you here is we took all the data that we had and we looked at anything above 20 dB of CINR and then looked at the effect of condition number. And as you can see, it's a pretty linear slide all the way from 0 dB all the way up to about 34 dB of condition number. That condition number does affect your MIMO throughput. You're going from about a theoretical maximum of 75 all the way down to about 40 megabits per second with the effect of condition number. But CINR would play a much higher role in MIMO throughput than what condition number does. And on the graph below, on the lower end, we looked at the CINR values of -5 and below. And like I said before, to have MIMO gain, you have to have good CINR. So what you can see from this chart on the bottom, you have pretty much flat MIMO, or I should say flat throughput unless you get to the very, very end. But again, you can look at the throughput and you can see that it's around 4 to 5 megabits per second only. And it's fairly flat until you get to a very, very high condition number where it goes down to about 3 to 4 dB. So really what plays the most important role for MIMO throughput and MIMO gain is CINR. It plays the most important role for throughput optimization. And increasing the condition number affects throughput for all CINR values, particularly at higher CINR, because at lower CINR you're not getting much MIMO gain anyway to begin with. One of the things about condition number, though, is it may be a difficult thing to adjust because you have to be able to change your antenna positioning slightly, and that can cause a lot of other effects in the area of the network. But hence, at least by taking these measurements, you can understand what's happening in your network, both from a CINR standpoint as well as a condition number standpoint. So with that, I'd like to summarize what we talked about today. From a MIMO perspective, MIMO analysis is important for understanding the overall throughput that can be achieved purely on based on RAN improvements. The reason for that is when you look at when you use a scanner to look at MIMO, you will be looking at the RAN. So therefore, anything that you see only applies to the RAN. You're not necessarily seeing any of the issues of the backhaul or the server loading that you would with the UE. The other important points to remember are that throughput is a function of CINR as well as condition number. And path measurements can be very, very important to understand any imbalance or misconnections. And we actually find that in probably about 1 or 2% of the new installations, you actually do find problems with misconnections. So consequently, having the ability to measure those paths can play a very important role in turning up a network. And the overall combination of MIMO parameters can really help you accurately identify throughput issues and detect the reasons for lower throughput. And to summarize some of the benefits of having a scanner receiver, number one, the ability to have high-speed data collections. This enables very, very detailed analysis of problems, and you can feed this high speed and all the data you collected into your propagation models to be able to get a very accurate picture of what your RF environment looks like, as well as have very high accuracy reporting correct PCIs, even when you have very low CINR values. The ability to have very high dynamic range to be able to accurately decode all the signals and help identify interferers. The ability to visualize a complete propagation profile for each sector. This helps in accurate design, benchmarking, and optimization. And the other nice thing is that scanners are passive. They don't drop a session. So when the UE drops a session, the scanner will continue to collect data to help you troubleshoot what's going on with that area. And with MIMO parameters, you also have the ability to analyze throughput even if the network throughput is capped, which we found in this case with the UE. So with that, I'd like to thank you for attending this webinar. What I have pictured here are some of our LTE posters that we provide at trade shows, as well as if you go onto our website. I have the URL here. We have a LTE physical layer poster, a LTE MIMO poster, and an LTE advanced poster, which talks about all these technologies as well as the bands and explains essentially what goes on at the physical layer, MIMO layer, and what's in LTE advanced. So please visit our website. This webinar will also be posted on our website in a few days. And now we'll start to entertain questions.
Okay, Jim, we've got a few minutes here. We have some questions posted during the presentation. One question is PCTEL scanner capable of measuring reference signals from different ports?
Yeah, I'm not totally sure what you mean by ports. But we do path measurements, so let's take for the example of 2x2 MIMO. You'll have 2 transmit antennas, and then you'll have 2 ports on your scanner and receiver for that. And each one of those ports have to be the same band. So if, let's say you're in a AWS band, what you'll do is you'll measure 4 separate paths there, because with 2x2 MIMO, you have a transmit path going to each of the 2 receivers from antenna port 1. Then from antenna port 2, on the transmit. On the E node B, you'll have another 2 paths going to each one of the receivers on a scanner. So we can measure all 4 of those paths and provide reference signal, receive power, RSRQ, receive quality, as well as the SINR or CINR on all of those paths that are where you're transmitting from the E node B to the receiver.
Okay. Next question, I think we answered part of this here, is is the MX capable of measuring multipath?
Yes. We actually do measure multipath. So I don't want to get into too many details of how we actually do that, but based on whether you have your cyclic prefix, whether it's extended or normal, and how much time it takes to get to the receiver, we can calculate what's a multipath and what's actually another PCI that might be coming from another tower.
And a follow-up to that question, how many receive antennas does the MX support?
So receive antennas, it really depends upon how you want to configure your MX. When you're doing MIMO, you essentially need an antenna for every port. So on a MX scanner, depending upon whether it's MIMO or not, you can have anywhere from 4 to 8 ports on an MX, and you would be using anywhere from 2 to 8 antennas in the worst case, where you have MIMO on every single port.
And how many channels, LTE channels, can the MX collect at the same time?
The MX can collect up to 24 channels at the same time. However, since the channel bandwidths are so wide in LTE, 5, 10, 20 megahertz, you will typically only see 1 or 2 active channels at any one time. It's really WCMA, UMTS, where you see a lot more channels that people are asking for.
There's one question on the post-processing. What tool was used to process the data?
Question is, which tool was used?
Yeah, what post-processing tool was used to process the data? I believe it was, I think it was Seahawk and MapInfo.
Yeah, we used CSV export to MapInfo to be able to process this data. But we also allow you to, there are a lot of companies that we provide comma-separated format to be able to go into their tools. Probably at least a half a dozen of them that we support.
Okay. There's a question on the building density for the drive test that was displayed. It was downtown Philadelphia.
Downtown Philadelphia, very high density, very high buildings, high rises, causing a lot of multipath, a lot of reflections.
There's a question if we're going to provide this a video after the session, and the answer is yes. We're doing another webinar tomorrow. We'll post it via YouTube and possibly via LinkedIn as well.
And it'll be on our website also in a few days. So if you go to PCTEL.com, RF Solutions, you'll be able to find this posted here in a few days.
Another question, how does the scanner know of cell loading in the network?
What it does is when you look at the RSRQ, you're actually looking at the power in each one of those resource elements. So you can kind of indicate that you have higher loading based on an RSRQ value. It's not going to give you a detailed analysis of what that loading is, because you really don't have a session with the with the tower or with the base station. So you can kind of get an indication of, based on all these values, of kind of what's going on in the network with these parameters that we measure.
Okay. These are all good questions. We've got a few more. Why is PCI interference a problem?
That's a good question. It can be a huge problem because if you have a lot of PCIs entering that area, like we did in this one particular area of Philadelphia, you don't necessarily have a dominant server, and as a result of that, you're getting a lot of handoffs, which results in failures. So having the ability to be able to look at different PCIs and be able to detect them can be very important. And in fact, we had one case in another area, not here, where they actually put a self-optimized network into that city, and the network was actually changing PCIs every single night. And as a result of that, we're seeing a lot of PCIs that had the same number, but they're coming from a different tower. So this self-optimized network was actually causing a lot of interference, and the scanner was able to detect that and to be able to find out that, yeah, this self-optimizing network isn't working as expected. It's actually causing two PCIs with the same number to be seeing in the same area, and they were having a lot of issues with the network as a result of this.
One more follow-up question on interference. Is LTE interference mainly on the uplink or downlink?
Are we really talking, there's two types of interference. You have, intercell interference coming from other towers, and there's also external interference. So in the case of, intercell interference, you're really looking at it on the downlink because that has such a high-powered signal coming from the cell tower that could be getting into other sectors. So consequently, you really want to look at a lot of the interference that's coming from the downlink on that. If it's coming from another LTE base station. If you're talking about external interference, such as motors and baby monitors and all that kind of thing, that is usually such low power that it only affects the uplink because the downlink is so dominant that you're not going to see that. So in that case, you have external interference. It's usually an uplink issue.
Okay, thanks, Jim. I think we've covered all the questions that were submitted, and we're just about out of time. So I wanted to thank our audience for joining us. I appreciate your time. If you have any questions, feel free to shoot Jim or myself an email. We'll be happy to get back to you. And I think that's it from here. So thanks all, and have a great day.
Thank you.